What is the fastest way to get the value of pi? I'm looking for the fastest way to obtain the value of pi. As a personal challenge, more specifically, I'm using ways that don't involve using hashtag-defined constants like m_pi, or hard-coding the number in. The program below tests the various ways I know of. The inline assembly version is, in theory, the fastest option, though clearly not portable. I've included it as a baseline to compare against the other versions. In my tests, with built-ins, the 4*ATAN 1 version is fastest on GCC 4.2, because it auto-folds the ATAN 1 into a constant, with FNO built-in specified. The ATAN 2 0-1 version is fastest. Here's the main testing program. PyTimes. C. Hashtag include less than math. H greater than. Hashtag include less than stdio. H greater than. Hashtag include less than time. H greater than. Hashtag define iters 10 million. Hashtag define testwith. X. Opening curly bracket backslash. Diff equals 0.0. Backslash. Time 1 equals clock. Backslash. 4. I equals 0. I less than iters. Plus I. Backslash. Diff plus equals. X. m_pi. Backslash. Time 2 equals clock. Backslash. Printf. %st equals greater than %e. Time equals greater than %f. N. Hash x. Diff. Diff clock. Time 2. Time 1. Backslash. Closing curly bracket. Static inline double. Diff clock. Clock underscore t time 1. Clock underscore t time 0. Opening curly bracket. Return. Double. Time 1 time 0. Clocks underscore per underscore sec. Closing curly bracket. Int. Main. Opening curly bracket. Int I. Clock underscore t time 1. Time 2. Double diff. Asterisk warmup. The ATAN2 case catches GCC's ATAN folding, which would asterisk optimize the backquote 4 asterisk ATAN 1 m_pi to a no-op. If FNO built-in asterisk is not used, asterisk testwith 4 asterisk ATAN 1 testwith 4 asterisk ATAN 2 1 1 hashtag if defined underscore nuke NN defined underscore I 386 underscore defined underscore AMD 64 underscore extern double FLDPI testwith FLDPI hashtag and if asterisk actual tests start here asterisk testwith ATAN 2 0-1 testwith ACOS -1 testwith 2 asterisk ASIN 1 testwith 4 asterisk ATAN 2 1 1 testwith 4 asterisk ATAN 1 return 0 closing curly bracket and the inline assembly stuff FLDPI C that will only work for x86 and x64 systems. Double FLDPI opening curly bracket double pi ASM FLDPI equals t pi return pi closing curly bracket and a build script that builds all the configurations I'm testing. Build.sh hash bin shish GCC03 wall CM32 OFLDPI 32 OFLDPI C GCCO3 wall CM64 OFLDPI 64, OFLDPI, C. GCCO3 wall F fast math M32O ptimes 1 to 32 ptimes, CFLDPI 32, O. GCCO3 wall M32O ptimes 2 to 32 ptimes, CFLDPI 32, OLM. GCCO3 wall FNO built-in M32O ptimes 3 to 32 ptimes, CFLDPI 32, OLM. GCCO3 wall F fast math M64O ptimes 1 to 64 ptimes, CFLDPI 64, OLM. GCCO3 wall M64O ptimes 2 to 64 ptimes, CFLDPI 64, OLM. GCCO3 wall FNO built-in M64O ptimes 3 to 64 ptimes, CFLDPI 64, OLM. Apart from testing between various compiler flags, I've compared 32-bit against 64-bit too because the optimizations are different. I've also tried switching the order of the tests around. But still, the ATAN2.0-1 version still comes out on top every time. The Monte Carlo method, as mentioned, applies some great concepts, but it is clearly not the fastest, not by a long shot, not by any reasonable measure. Also, it all depends on what kind of accuracy you are looking for. The fastest Pi I know of is the one with the digits hard-coded. Looking at Pi and Pi PDF, there are a lot of formulae. Here is a method that converges quickly. About 14 digits per iteration. Pi Fast, the current fastest application, uses this formula with the FFT. I'll just write the formula, since the code is straightforward. This formula was almost found by Ramanujan and discovered by Chudnovsky. It is actually how he calculated several billion digits of the number. So it isn't a method to disregard. The formula will overflow quickly and, since we are dividing factorials, it would be advantageous then to delay such calculations to remove terms. Where below is the Brent-Salomon algorithm. Wikipedia mentions that when A and B are close enough, then A plus B squared 4t will be an approximation of pi. I'm not sure what close enough means, but from my tests, one iteration got 2 digits, 2 got 7, and 3 had 15. Of course, this is with doubles, so it might have an error based on its representation and the true calculation could be more accurate. Let pi underscore 2 iters equals. Let rec loop underscore abtpi equals. If I equals 0, then a, b, t, p. Else, let a underscore n equals a plus b slash 2.0 and b underscore n equals sqrt. A, b, and p underscore n equals 2.0. P in. Let t underscore n equals t, p, a, of underscore n, asterisk, a, of underscore n, in, loop underscore a underscore n b underscore n t underscore n p underscore n. I1, in, let a, b, t, p equals loop underscore 1.0, 1.0, sqrt 2.0. 1.0.4.0, 1.0, iters in, a plus, b, asterisk, a plus, b, slash, 4.0, t. Lastly, how about some pi golf? 800 digits, 160 characters, int a equals 10000, b, c equals 2800, d, e, f. 2801. G. Main. 4. BC. F. B++ equals A. 5. 4. D equals O. G equals C2. C equals 14, print f. %.4d e plus d, a. E equals d percent a. 4. B equals c. D plus equals f. B. A, f. B. Equals d percent, g, d, equals g, b. D equals b. Closing curly bracket. I really like this program because it approximates pi by looking at its own area. IOCCC 1988. Westley, C. Hashtag define underscore f less than 00, fu. Int f equals 00, u equals 00. Main. F underscore u. Print f. Percent 1.3 f, n, 4. Asterisk f, u, u. F underscore u. Opening curly bracket. Underscore 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 underscore. Underscore 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 underscore. Underscore 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 underscore. Underscore 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 underscore. Underscore 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 underscore. Underscore 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 underscore. Underscore 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 underscore. Underscore 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 underscore. Underscore 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 underscore. Underscore 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 underscore. Underscore 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 underscore. Underscore 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 underscore. Underscore 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 underscore. Underscore 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 underscore. Underscore 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 underscore. Underscore 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 underscore. Closing curly bracket. Here's a general description of a technique for calculating pi that I learned in high school. I only share this because I think it is simple enough that anyone can remember it indefinitely. Plus it teaches you the concept of Monte Carlo methods, which are statistical methods of arriving at answers that don't immediately appear to be deducible through random processes. Draw a square and inscribe a quadrant, 1/4 of a semicircle. Inside that square, a quadrant with radius equal to the side of the square, so it fills as much of the square as possible. Now throw a dart at the square and record where it lands, that is, choose a random point anywhere inside the square. Of course, it landed inside the square. But is it inside the semicircle? Record this fact. Repeat this process many times, and you will find there is a ratio of the number of points inside the semicircle versus the total number thrown. Call this ratio x. Since the area of the square is r times r, you can deduce that the area of the semicircle is x times r times r. That is, x times r squared. Hence x times 4 will give you pi. This is not a quick method to use, but it's a nice example of a Monte Carlo method. And if you look around, you may find that many problems otherwise outside your computational skills can be solved by such methods. In the interests of completeness, a C++ template version, which, for an optimized build, will compute an approximation of pi at compile time, and will inline to a single value. Hashtag include less than iostream greater than. Template less than int I greater than. Struct sign. Opening curly bracket. A num value equals I%2 equals 0, 1, -1. Closing curly bracket. Template less than int I. Int j greater than. Struct pi underscore calc. Opening curly bracket. Inline static double value. Opening curly bracket. Return. Pi underscore calc less than I1. J greater than. Value. Plus pi underscore calc less than I1. J plus 1 greater than. Value. 2.0. Closing curly bracket. Closing curly bracket. Template less than int j greater than. Struct pi underscore calc less than 0. J greater than. Opening curly bracket. Inline static double value. Opening curly bracket. Return. Sign less than j greater than. Value asterisk 4.0. Slash. 2.0 asterisk j plus 1.0. Plus pi underscore calc less than 0. J minus 1 greater than. Value. Closing curly bracket. Closing curly bracket. Template less than greater than. Struct pi underscore calc less than 0. 0 greater than. Opening curly bracket. Inline static double value. Opening curly bracket. Return 4.0. Closing curly bracket. Closing curly bracket. Template less than int I greater than. Struct pi. Opening curly bracket. Inline static double value. Opening curly bracket. Return pi underscore calc less than I greater than. Value. Closing curly bracket. Closing curly bracket. Int main. Opening curly bracket. std. Coup. Precision. 12. Const double pi underscore value equals pi less than 10 greater than. Value. std. Coup less than pi tilde, less than pi underscore value less than std. endl. Return 0. Closing curly bracket. Note for I greater than 10. Optimized builds can be slow. Likewise for non-optimized runs. For 12 iterations I believe there are around 80 kcalls to value. In the absence of memoization, there's actually a whole book dedicated, amongst other things, to fast methods for the computation of pi and the AGM, by Jonathan and Peter Borwein, available on Amazon. I studied the AGM and related algorithms quite a bit. It's quite interesting, though sometimes non-trivial. Note that to implement most modern algorithms to compute pi, you will need a multi-precision arithmetic library. GMP is quite a good choice, though it's been a while since I last used it. The time complexity of the best algorithms is in O, M, N, log, N, where M, N, is the time complexity for the multiplication of two n-bit integers. M, N, equals O, N log, N, log, N, using FFT-based algorithms, which are usually needed when computing digits of pi, and such an algorithm is implemented in GMP. Note that even though the mathematics behind the algorithms might not be trivial, the algorithms themselves are usually a few lines of pseudocode, and their implementation is usually very straightforward. If you chose not to write your own multi-precision arithmetic, The following answers precisely how to do this in the fastest possible way, with the least computing effort. Even if you don't like the answer, you have to admit that it is indeed the fastest way to get the value of pi. The fastest way to get the value of pi is: choose your favorite programming language, load its math library, and find that pi is already defined there, ready for use. In case you don't have a math library at hand, the second fastest way, more universal solution, is look up pi on the internet, e.g. here, http www.evanderson.com/pi/digits/1000000 1 million digits. What's your floating point precision? Or here, http 3.1415926539979327571058209749945942.com/ or here, http en.wikipedia.org/wiki/pi. It's really fast to find the digits you need for whatever precision arithmetic you would like to use. And by defining a constant, you can make sure that you don't waste precious CPU time. Not only is this a partly humorous answer, but in reality, if anybody would go ahead and compute the value of pi in a real application, that would be a pretty big waste of CPU time. Wouldn't it? At least I don't see a real application for trying to recompute this. Also consider that NASA only uses 15 digits of pi for calculating interplanetary travel. TLDR. https twitter.com/rainmaker1973/status/1463477499434835968 JPL explanation https://www.jpl nasa.gov/edu/news/2016/3/16/how-many-decimals-of-pi-do-we-really-need/ The BBP formula allows you to compute the nth digit, in base 2 or 16, without having to even bother with the previous n1 digits first. Instead of defining pi as a constant, I always use ACOS, -1. This is a classic method. Very easy to implement. This implementation in Python, not the fastest language, does it. From math import pi. From time import time. Precision equals 10 ***6 hash higher value to higher precision. Hash lower value to higher speed. T equals time. Calc equals 0. For k and x range. 0. Precision. Calc plus equals -1. K slash 2 **k plus 1. Calc equals 4. Hash this is just a little optimization. T equals time. T. Print calculated. %.40f %calc. Print constant pi. %.40f %pi. Print difference. %.40f %abs. Calc pi. Print time elapsed. %s %reaper. T. You can find more information here. Anyway, the fastest way to get a precise as much as you want value of pi in Python is from gmpy import pi. Print pi. 3000. Hash the rule is the same as hash the precision on the previous code. Here is the piece of source for the gmpy pi method. I don't think the code is as useful as the comment in this case. Static char doc _pi. equals pi n returns pi with n bits of precision in an MPF object n. Quote, asterisk this function was originally from NetLib. Package BMP. By asterisk Richard P. Brent. Paulo Cesar Pereira de Andrade converted asterisk it to C and used it in his Lisp interpreter. Asterisk. Asterisk original comments. Asterisk. Asterisk sets MP pi equals 3.14159. To the available precision. Asterisk uses the Gauss-Legendre algorithm. Asterisk this method requires time O. Lane. T. M. T. So it is slower. Asterisk than MPPI if M. T. equals O. T asterisk 2. But would be faster for asterisk large T if a faster multiplication algorithm were used. Asterisk. See comments in MP mul. Asterisk for a description of the method. C. Multiple precision. Asterisk 0 finding and the complexity of elementary function. Asterisk evaluation. By R. P. Brent. In Analytic Computational. Asterisk complexity. Edited by J. F. Traub. Academic Press. 1976. 151 to 176. Asterisk rounding options not implemented. No guard digits used. Asterisk. Static pi object asterisk. Pig moppy underscore pi. Pi object self. Pi object args. Opening curly bracket. Pimf object pi. Int precision. MPF underscore TR underscore I2. R underscore I3. R underscore I4. MPF underscore TX. 1 underscore arg. Pi. I. And precision. If pi equals pimf underscore new. Precision. Opening curly bracket. Return null. Closing curly bracket. MPF underscore set underscore C. Pi to F. 1. MPF underscore init. X. MPF underscore set underscore UI. X. 1. MPF underscore init 2. R underscore I2. Precision. MPF underscore init 2. R underscore I3. Precision. MPF underscore set underscore D. R underscore I3. 0.25. MPF underscore init 2. R underscore I4. Precision. MPF underscore set underscore D. R underscore I4. 0.5. MPF underscore SQRT. R underscore I4. R underscore I4. 4. Opening curly bracket. MPF underscore set. R underscore I2. Pi to F. MPF underscore add. Pi to F. Pi to F. R underscore I4. MPF underscore div underscore UI. Pi to F. Pi to F. 2. MPF underscore mul. R underscore I4. R underscore I2. R underscore I4. MPF underscore sub. R underscore I2. Pi to F. R underscore I2. MPF underscore mul. R underscore I2. R underscore I2. R underscore I2. MPF underscore mul. R underscore I2. R underscore I2. X. MPF underscore sub. R underscore I3. R underscore I3. R underscore I2. MPF underscore SQRT. R underscore I4. R underscore I4. MPF underscore mul underscore UI. X. X. 2. Asterisk check for convergence asterisk. If MPF underscore CMP underscore C. R underscore I2. 0. And N. MPF underscore get underscore prec. R underscore I2. Greater than equals. Unsigned. Precision. Opening curly bracket. MPF underscore mul. Pi to F. Pi to F. R underscore I4. MPF underscore div. Pi to F. Pi to F. R underscore I3. Break. Closing curly bracket. Closing curly bracket. MPF underscore clear. X. MPF underscore clear. R underscore I2. MPF underscore clear. R underscore I3. MPF underscore clear. R underscore I4. Return. Pi object. Pi. Closing curly bracket. Edit. I had some problems with cut and paste and indentation. You can find the source here. If by fastest you mean fastest to type in the code, here's the golf script solution. 6666, minus 2%, 2 plus 0.2, at asterisk, 10.3, 2 plus, asterisk backquote 1000 less than tilde.